Hello and welcome to the Deep Discoveries channel. I'm glad you're here tonight. There is nothing you need to remember, nothing you need to follow closely, and nothing you need to solve. As you settle in, allow your breathing to soften and your thoughts to loosen their grip. Tonight we will drift through 100 facts about winter. Let them pass like falling snow, present for a moment, then gone. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, please consider liking and subscribing to the channel. It helps others find their way here too. In this space, winter becomes something else entirely. It becomes a season where physics speaks softly, where energy moves more slowly, and where hidden systems reveal themselves only when the noise fades. Snow, ice, and cold air are not pauses in nature's story. They are chapters written at a different pace. Cold air behaves differently from warm air because its molecules move more slowly and crowd closer together. When temperature drops, the same number of air molecules occupies less space, increasing density and weight. This denser air sinks toward the surface, spreading outward and pressing gently against the ground. The result is higher surface pressure and calmer, more stable conditions, especially on clear winter nights. This shift in density changes how air flows across landscapes. Cold air slides downhill into valleys, pools in low places, and moves like an invisible liquid shaped by terrain. Winds weaken near the surface while faster air may glide quietly above. These layered movements help explain why winter nights can feel still even when weather systems move overhead. Denser air also carries energy differently. It transfers heat more efficiently from skin, making cold feel sharper. It bends sound waves downward, allowing distant noises to travel farther. Even aircraft performance changes as wings generate lift in heavier air. Winter begins by quietly rearranging the atmosphere, replacing summer turbulence with order and weight. As cold air settles and holds its position, it sets the stage for another winter phenomenon, where layered air becomes trapped and motion slows further. During winter, the atmosphere can settle into layers that resist mixing. One of the most important of these patterns is a temperature inversion. Normally, air grows cooler with height, allowing warm surface air to rise and disperse. In an inversion, this pattern flips. Cold, dense air settles near the ground while warmer air rests quietly above it like a lid. This layered structure forms most easily on clear, calm winter nights when the ground rapidly loses heat. Once established, the inversion traps whatever is released near the surface. Exhaust, smoke, moisture, and fine particles accumulate instead of drifting away. Air can look hazy, smells linger longer, and breathing becomes subtly heavier. Chemical reactions also change inside this trapped layer. Some reactions slow in the cold, while others accelerate because gases remain concentrated. Light scatters differently through the dense mixture, sometimes giving winter air a muted color or glow. Inversions can persist for hours or days until wind, sunlight, or a passing storm breaks the seal. Until then, the atmosphere remains quietly stacked, holding its contents close to the ground. Within these still layers, tiny particles drift and wait, ready to play an unexpected role in the formation of snow itself. Every snowflake begins its life around something almost unimaginably small. High in the winter atmosphere, tiny particles float through the air: dust, salt, soot, pollen, and fragments carried from distant places. These particles are called ice nuclei, and without them, snow would struggle to form. When moist air cools enough, water vapor does not usually freeze on its own. Instead, vapor molecules cling to the surface of these microscopic seeds. Layer by layer, they arrange themselves into the familiar hexagonal structure of ice. As the crystal grows, it drifts through changing pockets of temperature and humidity, collecting more vapor along the way. The nucleus itself remains hidden at the center, often far smaller than the finished crystal. Yet it determines where growth begins and how the earliest structure forms. Different nuclei encourage freezing at slightly different temperatures, influencing when snow begins falling from a cloud. This quiet partnership between vapor and particle turns invisible air into visible snowfall. It is a reminder that vast winter landscapes often begin with interactions measured in microns. As each crystal continues its slow descent, the conditions it encounters will shape it further, ensuring no two paths through the sky are ever quite the same. No two snowflakes are exactly alike, not because nature avoids repetition, but because the conditions that shape each crystal are never perfectly the same. As a snow crystal falls, it passes through layers of air with subtly different temperatures and humidity levels. Each change alters how fast certain faces of the crystal grow, reshaping its structure moment by moment. Snowflakes begin with simple hexagonal symmetry, but complexity emerges as branches form and split. If the air is moist, branching accelerates. If it becomes drier, growth slows and edges sharpen. Even a fraction of a degree difference can redirect how vapor attaches to the crystal. Because the atmosphere is always shifting, the sequence of conditions each snowflake experiences is unique. Collisions with other crystals, brief rotations, and changes in fall speed further influence the final shape. By the time a snowflake reaches the ground, it carries a frozen record of its journey through the sky. Scientists study these structures to understand cloud dynamics and atmospheric behavior. The individuality of snowflakes is not randomness, but sensitivity. Winter reveals how small variations can echo outward into visible form. As countless unique crystals accumulate together, they create snowpacks that behave in surprisingly complex ways, influenced not just by shape, but by how crystals interact once they settle. In some of the coldest places on Earth, snow can fall from a sky without clouds. This phenomenon is known as diamond dust. It occurs when air near the ground becomes extremely cold, calm, and saturated with just enough water vapor. Instead of rising and forming clouds, the vapor freezes directly into tiny ice crystals suspended in the air. These crystals are much smaller than typical snowflakes and fall very slowly, often drifting sideways or seeming to hover. In sunlight, they sparkle intensely, creating a shimmering curtain that fills the air. At night, streetlights and moonlight turn diamond dust into glowing pillars and halos. Diamond dust forms most commonly in polar regions and high, cold interiors of continents. It depends on stillness. Even light wind can disrupt the delicate balance required for crystals to assemble. Because the crystals form close to the ground, they often coat surfaces evenly, creating frost-like layers rather than deep snow. This quiet precipitation blurs the line between weather and optics. It shows that winter does not always need towering clouds to create snowfall. Sometimes the cold itself is enough. In these silent conditions, the sky prepares for more energetic events, where motion and electricity briefly return to the frozen air. Although snowstorms are usually quiet, some winter storms generate lightning and thunder. This rare phenomenon is called thundersnow. It forms when strong upward motion develops inside a cold storm system, allowing ice particles to collide violently within clouds. These collisions separate electrical charges, building tension until it releases as lightning. The process resembles summer thunderstorms, but the environment is colder and denser, Snow crystals, soft hail called graupel, and supercooled droplets rub together in turbulent air. The result is a compact, highly energized cloud capable of producing thunder muted by falling snow. Thundersnow often occurs near large bodies of water, such as lakes or oceans, where relatively warm surfaces feed heat and moisture into cold air above. The contrast fuels vertical motion despite winter stability. Lightning flashes may appear diffuse, glowing softly through thick snowfall rather than sharply illuminating the sky. Because sound travels differently in cold air, thunder during a snowstorm can seem closer or deeper. These events are brief and localized, but powerful. They remind us that winter is not simply a season of stillness. Beneath calm surfaces, energy can still build, preparing the atmosphere for movement, sound, and light that will soon travel farther than expected through the cold night air. Winter storms do more than move snow across the ground. They move heat across entire regions. Large winter storm systems act like engines, drawing energy from areas where air or water is relatively warm and redistributing it into colder surroundings. As moist air rises within a storm, water vapor condenses and releases heat, fueling further motion and growth. That energy does not disappear. It travels with the storm, shaping weather far beyond its point of origin. Over oceans, winter storms can tap into stored heat at the surface and transport it inland. Over continents, they can pull cold air southward while pushing warmer air northward, reshaping temperature patterns across thousands of miles. These exchanges help balance Earth's climate, preventing extreme heat from building endlessly in one place. The movement of heat also affects wind patterns, pressure systems, and future storms. One winter system can influence the path and strength of the next. Snow cover left behind reflects sunlight, reinforcing cold conditions and extending the storm's influence after it has passed. Winter storms are not isolated events. They are part of a connected chain, quietly adjusting how energy flows around the planet. As that energy moves through cold air, it alters something more subtle, the way sound itself travels through the winter night. Cold air changes how sound moves through the atmosphere. When temperatures drop, especially near the ground, the air can become layered, with colder, denser air below and warmer air above. This structure bends sound waves downward instead of allowing them to rise and dissipate. As a result, sounds can travel much farther than they do in warmer seasons. On winter nights, distant noises such as trains, traffic, or voices may seem unusually close. The stillness of the environment enhances the effect. Snow absorbs many high-frequency sounds, reducing background noise and allowing lower tones to carry clearly. Without wind or insects, the acoustic landscape becomes simplified and open. The bending of sound is not caused by volume, but by physics. Changes in air density guide the path of sound waves, shaping where they travel. Valleys, frozen lakes, and open fields can act as natural corridors, carrying vibrations across long distances. This effect fades when temperatures rise or winds disturb the layered air. But during calm winter conditions, the atmosphere becomes an efficient transmitter of sound. In this quiet clarity, the air itself prepares for the next transformation, one where tiny changes in temperature decide whether snow falls lightly or gathers rapidly from the sky. Snowfall is highly sensitive to temperature, especially near the freezing point. A difference of just 1 or 2 degrees can determine whether moisture remains suspended in the air or falls quickly as snow. When air cools slightly below freezing, it becomes more efficient at converting water vapor into ice crystals. This efficiency can dramatically increase snowfall rates without changing the overall storm system. These small temperature shifts influence crystal shape and how flakes interact. In some conditions, snowflakes grow large and branch outward, clinging together as they fall. These clusters descend faster and accumulate quickly. In slightly warmer or drier air, crystals remain smaller and fall more gently, producing lighter snowfall. Because winter storms often hover near critical temperature thresholds, forecasting snow amounts becomes difficult. Tiny variations in altitude, cloud structure, or surface conditions can lead to major differences in accumulation across short distances. Snowfall intensity is not just about moisture, it is about how precisely the atmosphere crosses invisible thermal lines. Winter reveals how delicate balance can create dramatic results. As snow gathers on the ground, its presence begins to reshape the environment below, influencing light, temperature, and reflection in ways that slowly transform the landscape that comes next. Ice crystals suspended in winter air can bend and scatter light into precise geometric forms. These displays occur when countless microscopic crystals drift slowly while maintaining similar orientations. Plate-shaped crystals tend to settle flat, while column-shaped crystals align vertically, allowing light to enter and exit at predictable angles. When sunlight or moonlight passes through these crystals, it refracts and reflects, producing halos, arcs, and vertical pillars that appear to float above the horizon. The shapes depend on crystal geometry, light angle, and observer position. Because winter air can remain cold and stable for long periods, crystals persist long enough for these patterns to form. Halos often appear as pale rings around the sun or moon, while pillars rise like faint beams from bright light sources. These effects are not illusions, but optical consequences of frozen water interacting with light. Such displays are most common during very cold, calm conditions when clouds thin and crystals remain suspended. They fade quickly when temperatures rise or wind disrupts alignment. Winter briefly turns the sky into an optical instrument, using ice as its lenses. As light reshapes the sky above, the snow below begins reflecting that same light back upward, altering everything. Fresh snow dramatically changes how Earth handles sunlight. Each snow grain contains many flat facets that scatter incoming light in multiple directions. Because of this structure, new snow can reflect most of the sunlight that strikes it, a property known as high albedo. When landscapes brighten with snow, less solar energy is absorbed by the ground. Surface temperatures remain lower, and the air just above cools as well. This cooling strengthens stable air layers and reinforces winter conditions already in place. Snow, therefore, does not simply respond to cold, it helps maintain it. The reflective surface also increases contrast across the landscape. Shadows sharpen, distant features stand out, and nighttime environments grow brighter as artificial light bounces off the snowpack. Animals and humans alike experience altered visual conditions. As snow ages, its reflectivity slowly decreases. Grains bond together, surfaces smooth, and dark particles accumulate, allowing more sunlight to be absorbed. This gradual change influences melt timing in spring. Snow cover quietly participates in Earth's energy balance, acting as both mirror and regulator. As light reflects upward from the ground, it meets the cold air shaped earlier, setting the stage for clearer skies and sharper winter visibility in the quiet season. Winter skies often appear clearer and sharper than summer skies because cold air holds far less moisture. Water vapor is one of the main contributors to haze, scattering light and softening distant edges. When temperatures fall, excess moisture condenses or freezes out of the air, leaving a drier, more transparent atmosphere. With fewer suspended droplets, sunlight travels through the sky with less distortion. Distant mountains, buildings and stars appear crisper and colours deepen, especially near the horizon. The reduced humidity also limits cloud formation during calm periods, extending clear conditions for hours or days. This clarity is reinforced by winter's stable air layers. Without strong vertical mixing, particles remain settled instead of rising into the sky. Winds often weaken near the surface, preventing dust and aerosols from becoming airborne. Clear winter air also cools more efficiently at night, allowing temperatures to drop quickly once the sun sets. This rapid cooling further dries the atmosphere, strengthening the cycle. The visual calm of winter skies is therefore a physical outcome of temperature, moisture, and motion working together. As clarity expands outward, it prepares the eye for subtler optical effects, where cold air and light combine to gently bend the horizon itself slightly. Cold air can bend light and create winter mirages. When layers of air at different temperatures stack near the surface, each layer has a slightly different density. Light passing through these layers does not travel in straight lines. Instead, it curves gently as it moves from one layer to another. On very cold days, especially over snow-covered ground or frozen water, dense air near the surface sits beneath lighter air above. This arrangement can lift distant objects visually, making trees, buildings or shorelines appear higher, stretched or floating. The effect is known as a superior mirage, and it is most common in polar and winter environments. Unlike desert mirages, which create shimmering reflections, winter mirages often appear sharp and stable. The air is calm, the temperature contrast is steady, and the bending of light remains consistent for long periods. These illusions reveal how sensitive vision is to the structure of the atmosphere. Nothing physically moves, only the path of light changes. As winter flattens the landscape with snow and ice, it also reshapes how distance and horizon appear, preparing the eye for even more delicate interactions between frozen air and sunlight that quietly unfold during the deepest cold nights. Ice crystals act as tiny prisms that split and redirect sunlight. Each crystal has flat faces arranged in precise geometric angles. When light enters one face and exits another, it bends according to those angles, separating into subtle colors or forming structured beams. In winter, especially during very cold and calm conditions, the air can fill with countless suspended crystals. Many are shaped like plates or columns, and they tend to align themselves gently as they drift. This shared orientation allows light to interact with millions of crystals at once, producing coherent patterns rather than random sparkle. Halos form when light bends through hexagonal plates. Pillars appear when vertical columns reflect light upward or downward. Arcs and curves emerge when light follows more complex paths through rotating crystals. These displays depend on precision. A small change in temperature or wind can disrupt the alignment and erase the effect. That fragility makes winter optics brief and quiet. The sky becomes a canvas shaped by frozen geometry. As crystals slowly fall or dissolve, the patterns fade, guiding attention downward, where the low winter sun begins intensifying color along the horizon and easing the mind toward slower rhythms of observation and rest now. Low winter sun angles intensify the colors of sunrise and sunset. Because the sun stays close to the horizon, its light travels through a much thicker slice of atmosphere before reaching the ground. Along this longer path, shorter blue wavelengths scatter away, allowing warmer reds and oranges to dominate. Cold air enhances this effect. With less moisture and fewer aerosols suspended in the atmosphere, light scatters more cleanly. Colours appear deeper, edges sharper, and transitions smoother. Winter twilights often last longer as the sun moves slowly along a shallow arc. In polar and high-latitude regions, this geometry creates extended dawns and dusks that can persist for hours. The sky may glow with layered bands of pink, violet, and gold, shifting gradually as the sun barely rises or sets. Ice crystals high in the atmosphere can further shape these colours by reflecting and refracting the low-angle light. Pillars, arcs, and soft glows may accompany the colour display. These prolonged sunsets mark the rhythm of winter days. As daylight fades slowly, the landscape settles into shadow, preparing the senses for darkness, stillness, and the reflective brightness of snow under night skies that calm awareness and invite deeper rest tonight now. Snow changes the way nights look and feel by reflecting artificial light back into the sky. In cities and towns, streetlights, buildings, and vehicles normally send much of their light upward where it disperses into darkness. When snow covers the ground, that light strikes a bright surface and scatters outward instead of being absorbed. The result is a softer but wider glow that fills the night. This reflected light can make winter nights appear brighter even when skies are overcast. Clouds act like ceilings, catching the upward glow and spreading it evenly across the landscape. Streets, fields, and trees become gently illuminated without a single visible source. Shadows soften and distance becomes harder to judge. The effect alters both human perception and wildlife behaviour. Nocturnal animals experience longer periods of low-level illumination, while people often notice that familiar places feel strangely open and exposed at night. Snow also reduces contrast, blending edges together and flattening depth. As snow ages or melts, this brightness fades. Darker surfaces reappear, absorbing light and restoring deeper night skies. Until then, winter nights remain quietly luminous. This gentle brightness transitions naturally into another effect of frozen surfaces, where ice itself becomes so clear that it reshapes what we can see beneath our feet. Under calm and cold conditions, lake ice can form with remarkable clarity. When temperatures drop steadily and wind remains low, water at the surface freezes slowly enough to exclude most air bubbles and impurities. The result is ice that looks nearly invisible, creating the illusion of walking on open water. Clear ice forms best on lakes with clean water and minimal disturbance. As the surface freezes, dissolved gases are pushed downward instead of becoming trapped. Without bubbles to scatter light, the ice allows a direct view into the water below. Rocks, plants, and even fish may be visible through several inches of ice. As the ice thickens, internal stresses develop. Long cracks appear as dark lines, not because the ice is weak, but because it is expanding and contracting with temperature changes. These cracks often remain sealed, transmitting sound and vibration while preserving structural strength. Clear ice alters perception of depth and distance. The boundary between surface and water becomes ambiguous, quieting the sense of separation. This transparency invites the eye downward, where light begins bending subtly through the frozen layer itself, preparing the scene for optical distortions created by curved ice surfaces. Ice does more than allow light to pass through it. Under the right conditions, it bends and reshapes what is seen beneath. Clear ice with uneven thickness acts like a natural lens. Light travelling through thicker and thinner sections refracts at different angles, stretching, compressing, or shifting objects viewed below. On frozen lakes, this effect can make stones appear elongated, plants seem closer than they are, or dark features curve and ripple as the viewing angle changes. Even slight variations in ice thickness create noticeable distortion. As sunlight moves across the surface, these distortions drift slowly, giving the frozen world below a quiet sense of motion. This bending occurs because ice slows light more than air, but less than water. When light crosses between these materials, it changes direction. Curved surfaces intensify the effect, focusing or spreading light much like glass lenses. These distortions are subtle and silent. They do not announce themselves, but reward still attention. Winter transforms water into a transparent boundary that alters vision without sound or movement. As ice reshapes what the eye perceives below, the air above continues to influence perception as well, carrying sight farther than expected into distant winter landscapes. Winter air often allows people to see much farther than they can during warmer seasons. The primary reason is dryness. Cold air holds far less water vapor than warm air, and water vapor is one of the main causes of haze. When moisture condenses or freezes out of the atmosphere, fewer particles remain suspended to scatter light. With reduced scattering, light travels more directly from distant objects to the eye. Mountains appear sharper, skylines stand out more clearly, and stars seem brighter at night. This clarity is enhanced by winter's stable air layers. Without strong rising currents, dust and aerosols remain settled instead of being stirred upward. Snow on the ground can also improve visibility by increasing contrast. Dark objects stand out against bright backgrounds, and low sun angles illuminate terrain from the side, revealing shape and texture. Together, these factors give winter landscapes a sense of expanded depth. This clarity is not permanent. Wind, clouds, or warming temperatures quickly return moisture and motion to the air. But during calm winter days, the atmosphere becomes almost transparent. As visibility stretches outward, attention shifts upward as well. In the coldest conditions, suspended moisture can transform the air itself into a glowing structure, creating light displays that hover just above the ground. In extreme cold, fog can freeze while still suspended in the air. This phenomenon occurs when tiny droplets remain liquid below freezing, a state known as supercooling. When temperatures drop further or droplets encounter small disturbances, they freeze into countless microscopic ice crystals. These crystals drift slowly and reflect light efficiently. When illuminated by the sun, moon, or artificial lights, they form vertical pillars, arcs, or shimmering curtains. Streetlights may appear to stretch upward into the sky, while the sun can produce faint glowing columns that rise above the horizon. This frozen fog forms only under very specific conditions. The air must be calm, cold, and stable. Even light wind can disrupt the alignment of crystals and erase the effect. Because of this sensitivity, ice fog displays often appear suddenly and vanish just as quickly. The crystals may also settle onto surfaces, coating trees, wires, and buildings with delicate frost. These formations reveal the presence of invisible moisture that normally goes unnoticed. Frozen fog turns the lowest layer of the atmosphere into an optical medium, shaping light directly within the air we breathe. As attention returns from sky to ground, winter reveals one of its most unusual physical traits, hidden inside something as familiar as water itself. Water behaves in an unusual way when it freezes. Unlike most substances, it expands instead of shrinking as it turns from liquid to solid. This happens because water molecules lock into a rigid structure that takes up more space than the freely moving molecules in liquid form. As water cools, it becomes denser until it reaches about 4 degrees Celsius. Below that point, it begins to expand. When freezing occurs, hydrogen bonds force molecules into an open lattice, creating ice that is lighter than liquid water. This is why ice floats. This single property shapes winter ecosystems. Floating ice forms an insulating layer on lakes and rivers, protecting the liquid water below from freezing solid. Fish, plants, and microorganisms survive winter because ice remains at the surface instead of sinking. Expansion during freezing also generates force. Water trapped in cracks of rock, soil, or pavement can widen fractures as it freezes, gradually reshaping landscapes and structures. Water's expansion under cold conditions reveals how small molecular arrangements can control large-scale outcomes. As ice spreads across surfaces and floats quietly above darker water, it sets the foundation for deeper winter processes unfolding beneath frozen lakes and rivers. Ice floats because it is less dense than liquid water, a property that shapes nearly every winter landscape. As water freezes and expands into its crystalline structure, the molecules arrange themselves farther apart than they are in liquid form. This spacing lowers the overall density of ice, allowing it to remain buoyant. Floating ice forms a protective skin across lakes, ponds, and slow-moving rivers. Instead of freezing solid from the bottom up, water freezes from the surface downward. The ice layer insulates the water below, slowing heat loss and keeping deeper layers liquid throughout winter. Beneath this frozen ceiling, aquatic life continues at a slower pace, shielded from the harsh air above. The buoyancy of ice also affects how rivers and oceans behave. Ice sheets can move with currents and wind, piling up along shorelines or breaking into flows that drift and collide. These movements reshape coastlines and influence erosion patterns. This simple difference in density allows winter to preserve life rather than erase it. Without floating ice, many freshwater ecosystems would freeze completely each year. As ice settles into place on the surface, the water below begins to organize into layers, quietly rearranging temperature and chemistry beneath the frozen boundary. During winter, lakes develop stable layers that rarely mix until spring. As surface water cools, it becomes denser and sinks, displacing slightly warmer water below. This process continues until the lake reaches a uniform temperature just above freezing. Once ice forms at the surface, further mixing slows dramatically. Beneath the ice, water settles into layers based on temperature and density. The coldest water remains near the top, while slightly warmer, denser water rests below. Wind can no longer stir the surface, and sunlight penetrates only weakly through ice and snow. The result is a calm, stratified system. These layers affect oxygen, nutrients, and life. Algae may continue slow photosynthesis near the surface where light reaches, while deeper zones become darker and more chemically distinct. Nutrients released from sediments accumulate instead of circulating. This quiet separation can persist for months. When spring arrives and ice melts, the entire lake mixes suddenly, redistributing oxygen and nutrients in a dramatic turnover. Winter stratification turns lakes into still, layered worlds, each level holding its own conditions. While water organizes beneath the ice, the frozen surface itself begins interacting with flowing rivers, where ice introduces new dynamics and unexpected motion upstream. In winter, rivers can behave in ways that appear to defy gravity. Under certain conditions, surface water may briefly flow in the opposite direction of the river's usual course. This reversal does not last long, but it reveals how ice can temporarily reshape water movement. One cause is the formation of ice jams. As floating ice breaks apart and collects in narrow sections of a river, it can create a temporary barrier. Water continues arriving from upstream, raising the level behind the jam. Near the surface, pressure can force water to move backward as the system tries to equalize. Wind can also contribute. Strong, persistent winds blowing across wide river mouths or estuaries can push water inland, raising water levels enough to reverse surface flow for short periods. Once wind slackens or the jam breaks, normal flow resumes. To observers on the shore, the river seems to hesitate, pause, or change its mind. In reality, winter is briefly rewriting the rules of movement through ice, pressure, and resistance. As rivers adjust to frozen constraints, snow above them continues transforming. That snow will soon begin reshaping itself, even without melting, quietly disappearing into the air through another winter pathway. Snow does not always need warmth to disappear. Under cold, dry conditions, snow can transform directly from solid ice into water vapor through a process called sublimation. Instead of melting into liquid water, individual ice molecules gain enough energy to escape into the air, leaving the snow surface thinner without ever becoming wet. Sublimation occurs most efficiently when temperatures remain below freezing, sunlight is present, and the air is dry. Wind can accelerate the process by removing vapor from the surface, allowing more molecules to escape. In mountain regions and polar environments, large amounts of snow can vanish this way, even during prolonged cold spells. This process reshapes snow surfaces over time. Sharp edges form, grains grow angular, and subtle patterns appear as exposed areas lose mass faster than shaded ones. Snowpacks may shrink silently, misleading observers into thinking nothing has changed. Sublimation also influences water availability. Because vapor enters the atmosphere instead of soil or streams, some winter moisture never contributes to spring melt. Scientists track this loss carefully in regions dependent on snowpack for water resources. Snow sublimation reminds us that winter change does not always announce itself with dripping or flowing. Sometimes it happens molecule by molecule, quietly lifting frozen water into the sky, where it may later return in another form over distant ice-shaped seas. When ocean water freezes, it does not form a uniform solid. As sea ice grows, salt is mostly excluded from the ice crystal structure. This salt becomes concentrated in liquid pockets called brine channels, narrow networks of salty water that weave through the ice. Because salt lowers the freezing point, the brine remains liquid even in extreme cold. These channels expand and contract as temperatures change, opening pathways between the ice surface and the ocean below. Through them, salt, heat, and nutrients move slowly, shaping both ice structure and surrounding water. Brine channels also host life. Microorganisms adapted to cold and high salinity thrive inside these narrow spaces, forming active ecosystems within what appears to be solid ice. As sunlight returns late in winter, algae grow inside the channels, supporting larger food webs when the ice eventually melts. The brine can drain downward, increasing the density of seawater beneath the ice and influencing local ocean circulation. This process contributes to the formation of deep water masses that help drive global currents. Sea ice is therefore not frozen emptiness. It is a porous, living structure shaped by chemistry and temperature. Within and beneath it, gases produced by life continue rising, sometimes becoming trapped just below the ice itself. In winter, frozen lakes can trap methane gas beneath their surface, creating striking patterns of bubbles sealed inside clear ice. Methane forms when organic material at the lake bottom decomposes without oxygen. In warm months, this gas rises freely and escapes into the atmosphere. In winter, ice blocks its release. As methane bubbles rise, they collect beneath the ice. When freezing continues, the bubbles become trapped in layers, forming stacked disks or domes visible through clear ice. Each layer represents a separate pulse of gas released over time. The trapped methane does not disappear. It waits. When spring arrives and ice weakens, the gas escapes in bursts as the surface breaks apart. Scientists study these bubbles to understand methane emissions and winter biological activity beneath frozen water. The presence of methane shows that lakes remain chemically active even when sealed by ice. Microbes continue working slowly in cold, dark conditions, producing gases that reshape the frozen surface above. These frozen bubbles turn lakes into quiet archives of unseen life and chemistry. As gases accumulate beneath ice, they subtly stress the surface, setting up the cracking and movement that give winter ice its voice and vibration across frozen landscapes. Ice sheets store mechanical stress in much the same way a stretched object stores tension. As temperatures change, ice expands and contracts. Because large frozen surfaces such as lakes, rivers or sea ice are constrained by shorelines, currents and their own internal structure, this expansion cannot happen smoothly. Stress builds silently within the ice. When the stress becomes too great, it releases suddenly. The ice cracks, shifts or fractures, sending vibrations through both the frozen surface and the water below. These releases can produce sharp cracks, deep booms, or long resonant tones that travel great distances. Sensitive instruments often register these events as tiny seismic signals. The movement is not random. Cracks follow paths shaped by thickness, temperature gradients, and existing weaknesses. Some fractures propagate for hundreds of meters, while others branch into intricate patterns. After release, the ice settles again, only to begin storing stress once more as temperatures continue to fluctuate. This constant cycle of tension and release means ice is never truly still. Even on calm winter nights, frozen surfaces are adjusting invisibly. As stress redistributes across ice sheets, it prepares the frozen world for gradual surface changes above, where snow continues to accumulate, storing not energy, but vast amounts of frozen water. Snowpack acts as one of Earth's largest temporary freshwater reservoirs. Over the course of winter, falling snow accumulates layer by layer, trapping enormous amounts of water in frozen form. What appears light and airy on the surface can represent meters of stored water when compressed and melted. As snow settles, its structure changes. Individual crystals bond together, air spaces shrink, and density increases. Scientists measure snowpack not just by depth, but by snow water equivalent, the amount of liquid water the snow contains. In mountainous regions, this stored water becomes the primary source for rivers, reservoirs, and agriculture during spring and summer. The timing of snowmelt matters. Gradual warming allows water to seep slowly into soil and streams. Rapid warming can overwhelm systems, causing floods. Snowpack also regulates temperature by insulating the ground and reflecting sunlight, delaying melt until conditions shift. Snow does not simply fall and wait. It evolves throughout winter, responding to temperature, sunlight, and pressure. Long before melting begins, the snowpack is quietly shaping future water availability. Along coastlines where snow meets ice and wind, frozen water takes on entirely different forms sculpted by motion rather than accumulation. Along cold coastlines, ice can be shaped into wave-like formations that resemble frozen motion. These shapes are not liquid waves caught mid-break, but structures formed gradually through repeated freezing, wind, spray, and sublimation. Ocean spray thrown into cold air freezes on contact, layering ice onto existing forms. Over time, wind sculpts this ice, removing material from exposed areas while allowing protected sections to grow. The result can resemble crests, ridges, or rolling shapes similar to waves. Slush ice pushed together by currents can also pile into rounded formations that harden as temperatures remain low. These formations change constantly. A shift in wind direction, temperature, or tide can erode one shape and build another nearby. What looks solid and permanent is often temporary, reshaped within days or hours. Coastal ice demonstrates how winter works through repetition rather than speed. Instead of freezing a moment, it accumulates history. Each layer records past conditions, frozen into form. As wind and cold continue their quiet work along shorelines, inland landscapes respond differently, where rock, soil, and ice begin interacting through cycles of freezing and release deep within the ground. Freeze-thaw cycles slowly fracture rock through a process known as frost wedging. When temperatures rise above freezing, liquid water seeps into tiny cracks and pores in stone. As temperatures fall again, that water freezes and expands, exerting pressure on the surrounding rock. Each cycle widens the crack by a small amount. The force involved is significant. Expanding ice can generate pressures strong enough to split solid stone over time. The process works gradually, requiring repetition rather than speed. Winter provides ideal conditions because temperatures often hover around the freezing point, allowing frequent transitions between liquid and solid states. Rock type matters. Stones with existing fractures, layered structures, or porous textures are especially vulnerable. Over many seasons, frost wedging breaks larger rocks into smaller fragments, contributing to soil formation and reshaping slopes and cliffs. This process also affects human structures. Pavement, foundations, and retaining walls experience similar stress when moisture freezes within cracks. Engineers account for frost action when designing in cold climates. Frost wedging reveals winter's quiet persistence. Nothing dramatic happens in a single night, but change accumulates steadily. As rock breaks apart at the surface, the ground beneath responds as well, where frozen soil begins exerting its own upward forces during the coldest months of the year. Frozen soil can rise upward with enough force to move heavy objects, a process called frost heave. It begins when moisture within the ground migrates toward freezing fronts. As water freezes, it expands and forms ice lenses, layered sheets of ice that grow by drawing in more liquid water from surrounding soil. As these ice lenses thicken, they push the soil above them upward. Roads can buckle, fence posts can tilt, and building foundations may shift slightly out of alignment. The amount of movement depends on soil type. Fine-grained soils like clay and silt hold more water and experience stronger heaving, while sandy soils are less affected. Frost heave is most common in regions with repeated freeze-thaw cycles rather than continuous deep cold. Each cycle adds movement, gradually altering the surface. When thaw arrives, the ground does not always settle evenly, leaving behind cracks or uneven terrain. This upward motion reminds us that winter acts not only on the surface, but from within the ground itself. As frozen soil lifts and shifts, it quietly redirects water pathways below, influencing how meltwater will later move across the landscape when spring begins to loosen winter's grip. Frozen ground changes the way water flows long before snow begins to melt. When soil freezes, it becomes far less permeable, preventing liquid water from soaking downward. As a result, meltwater and winter precipitation are forced to move across the surface or along shallow pathways rather than infiltrating deeply. This redirection reshapes drainage patterns. Small streams may shift position, surface runoff may increase, and water can pool in places that remain dry during warmer months. Ice within soil can also lift and tilt ground layers, subtly altering slopes and channels. During winter, ice can anchor fallen branches, rocks, and debris in place. These obstructions remain fixed until thaw, guiding water into new routes once melting begins. By the time spring arrives, the landscape has already been rearranged beneath the snow. Frozen ground also affects erosion. Early meltwater flows over hardened surfaces, increasing its ability to carve channels and transport sediment. These effects accumulate year after year, slowly influencing river paths and valley shapes. Winter's influence on water movement begins quietly, hidden beneath ice and snow. As frozen soil loosens its hold, the pathways prepared during cold months guide the next stage of seasonal change, where snow itself begins transforming without flowing at all. Erosion does not stop in winter, but it follows different rules than it does in warmer seasons. When the ground freezes, soil particles lock together, temporarily resisting movement. This can slow erosion during periods of deep cold, but it also sets the stage for sudden change when temperatures fluctuate. Freeze-thaw cycles weaken surfaces over time. As water expands within soil and rock, it loosens material that will later be carried away. When brief thaws occur, meltwater often flows over frozen ground instead of soaking in, increasing its speed and erosive power. This fast-moving surface water can strip away loosened soil, carve shallow channels, and transport sediment downslope. Snow cover further complicates the process. Snow protects soil from direct wind erosion, but it also concentrates meltwater into specific pathways when it begins to disappear. These focused flows can cause localized erosion that would not occur in evenly saturated ground. Winter erosion tends to be episodic rather than constant. Long periods of apparent stillness are punctuated by brief moments of intense change. Over many years, these moments add up, shaping slopes, stream banks, and valley floors. Winter's slower pace hides its impact, but the ground remembers each cycle. As erosion subtly reshapes the surface, frozen water above it continues forming rigid sheets, where stress and fracture create patterns that mirror far larger geological forces. Frozen surfaces often fracture into patterns that resemble miniature versions of tectonic plates. When ice forms across lakes or rivers, it behaves like a thin, rigid sheet. As temperatures drop, the ice contracts. When it warms, it expands. These movements generate stress that must be released through cracking. Rather than breaking randomly, the ice often fractures along straight lines that intersect at angles, forming plate-like sections. Where sheets collide, ridges can rise. Where they pull apart, open cracks called leads appear. These patterns shift continuously as conditions change, creating a dynamic surface that reorganizes itself throughout winter. Water movement beneath the ice adds complexity. Currents push upward against weak points, while changing water levels bend the ice from below. The result is a constantly adjusting system that records stress, motion, and release. Scientists study these fracture patterns to better understand how materials behave under tension. Similar principles apply to Earth's crust. though on vastly different scales and timescales. For observers, frozen lakes become visible maps of force and balance. Each crack marks a moment of adjustment. As ice continues responding to temperature and pressure, it preserves the history of winter's motion until snowfall slowly covers the surface, storing a different kind of record layer by layer. Each snowfall leaves behind a layered record of winter weather. As snow accumulates, individual storms deposit snow with distinct properties shaped by temperature, wind, and humidity. Over time, these layers compress but remain identifiable by differences in grain size, density, and structure. Calm snowfalls often produce light, fluffy layers with delicate crystals. Windy storms create denser layers as snow is broken and packed together. Brief warm periods can form thin crusts when surface snow partially melts and refreezes. Even airborne dust or pollen can leave faint coloured lines within the snowpack. Scientists dig snow pits to read these layers much like pages in a book. Each layer tells a story about conditions at the time it formed. These records help researchers understand avalanche risk, climate patterns, and how snowpack will behave as it warms. As winter progresses, the snowpack changes internally. Heat and vapor move through it, reshaping grains and strengthening or weakening layers. What began as falling crystals becomes a complex, evolving structure. Snow quietly archives the season above it. While ice fractures record stress and motion, snow layers record time itself. As these layers deepen, they begin the slow transformation that leads from seasonal snowfall to something far more permanent, preserved deep within ice. In places where snow survives year after year, it slowly transforms into ice that preserves the chemistry of the atmosphere itself. As new snow falls, it buries older layers beneath it. Over time, pressure compresses the lower snow, squeezing out air and turning it into solid ice. Tiny bubbles of ancient air become trapped inside, sealed away from the modern world. These frozen layers form ice cores, which scientists drill from glaciers and ice sheets. Each layer corresponds to a specific period in time, sometimes representing a single year or even a single season. Inside the ice, researchers find traces of carbon dioxide, methane, volcanic ash, dust, and sea salt. Together, these materials reveal how Earth's atmosphere has changed across centuries and millennia. The preservation works because cold slows chemical reactions and prevents decay. Once sealed, the trapped gases remain remarkably stable. By analysing them, scientists reconstruct past temperatures, storm patterns, and even distant wildfires. Ice cores are not just frozen water. They are time capsules created by winter's persistence. As snow continues to layer and compress, it transforms temporary weather into permanent record, storing the memory of air itself. Beneath these archives, the cold also preserves physical features at the surface, holding fragile geological forms in place until warmth returns. Extreme cold can temporarily preserve delicate geological features that would otherwise erode quickly. When temperatures remain below freezing, moisture within soil and rock turns to ice, binding particles together. This frozen cement stabilizes loose material, preventing wind or water from carrying it away. In winter, cliffs may hold thin flakes of stone that would crumble during rain. Slopes remain intact because frozen ground resists movement. Even footprints, animal tracks, and fine surface textures can persist for weeks when locked into frozen soil. The cold effectively pauses erosion by limiting the mobility of water, the primary driver of surface change. This preservation is temporary. As soon as thaw begins, the stabilizing ice disappears. materials loosen, and erosion resumes, often rapidly. The contrast between winter stability and spring change can be dramatic, with entire surfaces reshaping in a short time. Winter therefore acts as a geological pause button rather than a permanent solution. It does not stop change, but delays it, storing energy and instability for later release. While the ground remains still and preserved, temperature differences across the surface become easier to detect. With heat flow slowed and movement reduced, winter reveals hidden thermal patterns that remain invisible during warmer, more active seasons. Winter conditions make subtle thermal patterns across landscapes easier to observe. When temperatures drop sharply, different materials release heat at different rates. Rock, soil, vegetation, water, and built surfaces each respond to cold in their own way, creating a patchwork of temperature contrasts. During clear winter nights, heat escapes rapidly into the atmosphere. Areas that retain warmth, such as rocky outcrops, buildings, or moist ground, stand out against colder surroundings. These differences are often invisible in summer, when sunlight and atmospheric mixing blur contrasts. In winter, reduced background heat sharpens them. Scientists use winter conditions to study energy flow through the ground and built environments. Thermal imaging reveals heat leaks in buildings, groundwater movement beneath soil, and even wildlife activity beneath snow. Animals leave warm traces, and buried pipes or springs appear as faint glowing lines against frozen ground. These patterns also influence local weather. Warm patches can disrupt frost formation or alter fog behavior. Small differences scale upward, shaping microclimates across short distances. Winter acts like a natural spotlight, stripping away thermal noise and revealing structure beneath the surface. As these patterns emerge, they connect surface cold with deeper history, where frozen ground preserves not just heat, but traces of life from far earlier climates locked beneath tundra and ice. In regions where the ground remains frozen for thousands of years, winter preserves traces of ancient ecosystems beneath the surface. Permafrost, soil that stays frozen year-round, acts as a natural freezer that slows decay almost to a stop. Within it, scientists have discovered remnants of forests that once grew where tundra now dominates. Tree trunks, roots, leaves, and pollen remain remarkably intact, sealed away by ice and the absence of oxygen. These frozen layers record past climates, showing that regions now locked in cold once supported thriving woodlands during warmer periods. By studying these preserved materials, researchers reconstruct ancient temperatures, rainfall patterns, and vegetation shifts. Permafrost preservation is passive rather than protective. It does not maintain ecosystems, but holds them in suspension. When thaw occurs, even briefly, decay resumes quickly. This contrast highlights how effectively cold halts biological and chemical change. Winter's ability to preserve extends beyond the present season, reaching deep into Earth's past. The frozen ground becomes a library of former landscapes, each layer storing evidence of how climate has shifted over time. As these ancient records rest beneath the surface, life above continues adapting to modern winters. Snow insulates living systems, allowing biological activity to persist quietly even when the land appears frozen and still. Snow acts as an insulator that protects the ground beneath it from extreme cold. Although snow feels cold to the touch, the air trapped between its crystals slows heat loss from the soil. A deep snowpack can keep ground temperatures near freezing even when the air above drops far lower. This insulation creates a protected zone just below the surface. Plant roots avoid lethal temperatures, soil microbes continue slow metabolic activity, and nutrients remain available for spring growth. Without snow, sudden cold snaps would penetrate deeper, damaging ecosystems long before winter ends. Small animals take advantage of this insulated space. Mice, voles, and insects tunnel beneath the snow, moving through a hidden world where temperature remains stable and predators are blocked. This subnivean environment supports feeding, movement, and survival through the coldest months. The insulating effect also shapes landscapes. Soils under snow freeze more slowly and thaw later, influencing water movement and erosion patterns in spring. Snow therefore moderates not just temperature but timing. Winter's quiet blanket keeps life active below the surface. While snow shelters ecosystems beneath it, animals above ground respond differently, reshaping their internal rhythms to survive the prolonged cold. Many animals survive winter by dramatically lowering their metabolic activity. This strategy reduces energy demand when food is scarce and temperatures are low. Instead of maintaining normal body functions, these animals slow heart rate, breathing, and cellular processes to a fraction of their usual pace. Hibernation varies by species. Some mammals enter deep torpor, allowing body temperature to drop close to the surrounding environment. Others remain slightly active, waking periodically to adjust position or eliminate waste. In all cases, fat reserves accumulated during warmer months provide the primary energy source. This metabolic slowdown is carefully regulated. Hormones shift, enzymes change efficiency, and cells alter how they use fuel. The process is not sleep, but a controlled physiological state shaped by evolution. Cold itself supports this strategy. Lower temperatures reduce chemical reaction rates, making it easier for bodies to operate slowly without damage. Winter provides the environmental conditions that make hibernation possible. As animals retreat inward and reduce activity, winter ecosystems grow quieter above ground. Yet beneath ice, snow, and soil, life continues adapting in other ways, where some organisms do not avoid freezing at all, but survive by enduring it directly within their own tissues. Some animals survive winter by tolerating the formation of ice inside their bodies. Certain amphibians, insects, and invertebrates allow parts of their tissues to freeze when temperatures fall far below zero. Rather than preventing ice entirely, they control where and how it forms. These animals produce specialized compounds, such as glucose or glycerol, that act as cryoprotectants. These substances limit ice growth, protect cell membranes, and prevent lethal dehydration. Freezing is directed to spaces outside cells, reducing internal damage. During this time, heartbeat, breathing, and brain activity may nearly stop. From the outside, these organisms appear lifeless. Yet when temperatures rise, ice melts, circulation resumes, and normal activity returns. The transition can happen within hours. This strategy requires extreme biochemical precision. Ice must form slowly and in controlled locations. Sudden freezing would still be fatal. Winter provides the gradual cooling necessary for this delicate balance. Freeze tolerance shows that winter survival is not always about avoiding cold. Sometimes it means meeting it directly. While some animals freeze in place, others remain active beneath the ice, where liquid water behaves in ways that quietly protect entire aquatic ecosystems. Water's unique density behavior allows lakes and ponds to remain liquid beneath ice during winter. As water cools, it becomes denser until it reaches about 4 degrees Celsius. Below that point, it becomes less dense again, allowing colder water to float above warmer water. When winter arrives, surface water cools first and sinks until the entire water column reaches this dense state. Further cooling causes the coldest water to stay at the surface, where it eventually freezes. Ice then floats, forming a protective lid over the liquid water below. This layering prevents lakes from freezing solid. Beneath the ice, temperatures remain stable, allowing fish, amphibians, and microorganisms to survive the winter. The ice also blocks wind, reducing mixing and conserving heat. Without this unusual property, winter would eliminate aquatic life in many regions each year. Instead, water itself becomes a shield, preserving ecosystems through the coldest months. As liquid water continues moving quietly below ice, its chemistry also changes. With limited mixing and light, winter lakes develop layered environments that shape biological activity long before spring returns. Winter lakes often form stable layers that remain separate for months. Once ice covers the surface, wind-driven mixing stops. Light penetration decreases, and temperature differences between layers persist. The result is a stratified system where water near the surface behaves very differently from water below. Oxygen levels can decline in deeper layers because fresh oxygen from the air cannot easily enter. At the same time, nutrients released from sediments accumulate near the bottom. Microbial activity continues slowly, altering chemical balances in isolation. In clear ice, some sunlight still penetrates, allowing algae to remain active near the surface. Deeper zones remain dark and cold, creating distinct habitats within the same lake. These conditions shape which organisms survive the winter and how they behave. When spring arrives and ice melts, the entire system mixes suddenly. Oxygen and nutrients redistribute, triggering bursts of biological activity that define the start of the growing season. Winter stratification quietly prepares lakes for renewal. As frozen surfaces release their hold, energy stored beneath the ice rises upward, just as winter air above continues shaping sound, light, and motion in unexpected ways. Winter air can carry sound much farther than summer air. This happens because cold air changes the way sound waves bend as they move through the atmosphere. On calm winter nights, the ground cools quickly while the air above remains slightly warmer, creating a temperature inversion. Under these conditions, sound waves curve downward instead of dispersing upward. Rather than fading into the sky, they are guided along the surface, allowing noises to travel long distances with surprising clarity. A train horn, a barking dog, or cracking ice may sound closer and sharper than it truly is. Snow cover also contributes. Fresh snow absorbs many high-frequency sounds, reducing background noise. With fewer competing sounds and less wind, the environment becomes acoustically clean. What remains travels farther. This effect is not psychological. It is a physical consequence of temperature, air density, and atmospheric layering. Winter reshapes the invisible structure through which sound moves. The result is a quieter world that paradoxically carries distant noise more clearly. As winter sharpens sound, it also alters how light behaves in cold air, bending and scattering it in ways that make familiar landscapes appear subtly unfamiliar. Cold air can change how light bends across the landscape, producing winter mirages. When the air near the ground becomes extremely cold and dense, and warmer air rests above it, light rays curve as they pass through these layers. Objects may appear lifted, stretched, or displaced from their true position. These effects are most common over flat, snow-covered terrain where surface cooling is uniform. Distant trees, buildings, or mountains can seem taller or closer than they really are. In rare cases, objects below the horizon become visible through a phenomenon called looming. Unlike desert mirages caused by heat, winter mirages arise from cold. The physics is the same, but the conditions are reversed. Light follows the path of changing air density, quietly reshaping reality. Because winter air is often clear and dry, these distortions can appear sharp rather than hazy. They come and go without warning, lasting only as long as the temperature layers remain stable. Winter's optical tricks remind us that even vision depends on the environment. As light bends through cold air, ice crystals above begin scattering it into shapes that belong only to winter skies. Ice crystals suspended in winter air can create halos, pillars, and arcs around the sun and moon. These optical displays form when light passes through tiny hexagonal ice crystals drifting in cold, stable air. The crystals act like microscopic prisms and mirrors. Different shapes produce different effects. Flat, plate-shaped crystals create halos and light pillars. Column-shaped crystals generate arcs that curve across the sky at precise angles. The geometry of each display depends on crystal orientation and the height of the light source. These phenomena require very specific conditions: cold temperatures, calm air, and the right crystal structure. That is why they appear most often in winter and rarely during warmer months. Unlike clouds made of liquid droplets, ice crystal clouds interact with light in rigid, predictable ways. This gives winter skies their sharp, mathematical beauty. For a brief moment, the sky becomes an instrument shaped by frozen air. As these displays fade, the same crystals settle slowly downward, returning winter's attention from light above to the quiet chemistry unfolding at ground level. Extremely cold winter air can alter the chemistry of the atmosphere near the ground. When temperatures drop and winds become light, the lower atmosphere often separates into layers, with dense cold air pooling close to the surface and warmer air resting above it. This structure limits vertical mixing and creates a trapped environment. Within this shallow layer, gases and particles behave differently. Pollutants from vehicles, heating systems, and natural sources accumulate instead of dispersing. Chemical reactions that depend on temperature slow down, while others become more efficient because molecules remain concentrated in a confined space. Nitrogen oxides, ozone, and fine particles can reach higher concentrations during calm winter nights. Even natural emissions from soil and vegetation linger longer, subtly changing the composition of the air we breathe. These shifts can influence visibility, scent, and the way light scatters, sometimes giving winter haze a distinct texture or colour. Winter does not merely cool the air, it reorganises it, reshaping the invisible chemical landscape close to the ground. As this altered air settles and stills, moisture within it responds as well, sometimes forming ice not in clouds above, but directly in the open air itself. In some of the coldest winter conditions, ice crystals can form in clear skies without clouds. This phenomenon, often called diamond dust, occurs when air near the ground is extremely cold, calm, and still contains a small amount of water vapor. Instead of rising to form clouds, water molecules arrange themselves directly into tiny ice crystals, often nucleating around microscopic particles. These crystals are small and light, falling so slowly that the air seems filled with a shimmering mist. Sunlight or streetlights catch their flat surfaces, producing sparkling curtains of light. Diamond dust is most common in polar regions and high-latitude winters, but it can appear anywhere temperatures drop low enough. The sky remains blue, uninterrupted, while ice falls quietly from invisible origins. This type of precipitation blurs the boundary between weather and optical display. It forms not from towering clouds, but from stillness itself. As these crystals drift downward, they remind us that winter can produce snowfall without storms, setting the stage for sound, scent, and motion to change once more. as frozen air continues shaping how energy travels. Winter air density can influence how energy moves through the atmosphere, even if living organisms do not consciously adjust to it. Cold air is denser than warm air, which changes how forces like drag and lift behave for moving objects, including wind-driven particles and flying animals. While birds primarily adjust their flight behavior in response to wind patterns, food availability, and the absence of thermal updrafts, denser air still subtly affects the physics of movement. Increased density can raise both lift and drag, altering how efficiently wings, leaves, and airborne particles travel. This balance means winter skies behave differently from summer ones. Dust, ice crystals, and snow grains respond more strongly to small air movements. Wind-driven transport changes altitude and distance, reshaping how materials move across regions during cold months. The atmosphere becomes heavier, quieter, and more resistant. Energy moves more deliberately. These subtle shifts influence everything from storm structure to how sound and scent travel. As winter air thickens and settles, it continues guiding motion in restrained ways, preparing the atmosphere for the larger reorganizations that occur when storms arrive and redistribute heat across vast distances. Winter storms play a major role in moving heat across the planet. Large cold season systems often draw energy from warm ocean surfaces and transport it into colder regions. As moist air rises within these storms, heat is released when water vapor condenses into clouds and precipitation. This transfer reshapes atmospheric circulation. Heat that originated in tropical or temperate oceans can influence temperatures thousands of miles away. At the same time, cold air masses are pushed southward, redistributing energy in the opposite direction. Winter storms act as moving exchanges, balancing temperature differences across hemispheres. These processes affect jet stream patterns, storm tracks, and regional climate variability. A single strong system can shift long-term weather patterns for weeks. The movement is not chaotic, but governed by pressure gradients, Earth's rotation, and contrasts between warm and cold air. Winter storms therefore do more than produce snow or wind. They participate in planetary-scale energy management, quietly redistributing heat to maintain balance. As these systems move across land and sea, their interaction with frozen surfaces below further alters outcomes, especially where snow cover reflects sunlight and reinforces cold conditions. Snow-covered landscapes reflect a large portion of incoming sunlight back into space. This reflectivity, known as albedo, is much higher for fresh snow than for soil, vegetation, or water. As a result, snow-covered regions absorb less solar energy and remain cooler. This cooling effect feeds back into the climate system. Lower surface temperatures reinforce cold air masses, helping snow persist longer. In some cases, widespread snow cover can strengthen high-pressure systems that influence weather far beyond the snowy region. Even small changes in snow extent can alter regional temperatures. When snow retreats early, darker ground absorbs more heat, accelerating warming. When snow spreads, cooling intensifies. Scientists monitor snow cover closely because it plays a powerful role in seasonal and long-term climate behavior. Winter landscapes actively shape the energy balance of the planet. As snow reflects sunlight upward, the air above becomes colder and more stable, influencing how storms move and how moisture returns to the ground in the form of carefully layered snowfall. Snowpack holds vast amounts of frozen water that will later feed rivers and aquifers. Although snow often appears light and airy, its total water content can be immense. As snow accumulates, crystals compress and bond, increasing density over time. Mountain snowpack acts as a natural reservoir. During spring, gradual melting releases water steadily, sustaining ecosystems, agriculture, and human communities. If melting happens too quickly, flooding can occur. If snowpack is thin, drought may follow. The structure of snowpack controls how water flows. Meltwater moves through internal channels shaped by temperature, sunlight, and layer strength. These pathways guide water towards specific exit points. Winter quietly stores water while determining how it will be delivered months later. Snow is not just frozen precipitation, but delayed rainfall. As this stored water waits beneath winter skies, the frozen surfaces above continue interacting with wind, reshaping snow into moving forms that echo landscapes usually associated with heat and sand. Snow can form dunes that migrate across the landscape, much like sand dunes in deserts. When snow is dry and loose, wind pushes it into ridges that grow, shift, and reorganize with each gust. These snow dunes, sometimes called sastrugi, can range from subtle ripples to sharp, sculpted formations. Because snow is lighter than sand, even moderate winds can shape it. The orientation of dunes reveals prevailing wind direction and strength. Over time, these features move slowly across open fields, frozen lakes, and polar plains. Snow dunes influence travel, insulation, and melt patterns. Wind-scoured areas expose ground to deeper cold, while drifts trap warmth beneath them. These variations shape ecosystems at small scales. The resemblance between snow dunes and desert dunes highlights shared physical principles. Both arise from granular materials responding to fluid motion. Winter landscapes, shaped by wind, mirror hotter environments in form, if not in temperature. As these snow structures shift and settle, they influence how sound and motion behave across frozen surfaces, continuing winter's quiet transformation of space itself. Frozen lakes can transmit vibrations across long distances. A broad ice sheet behaves like a rigid membrane. When it cracks, shifts, or is struck, vibrations spread outward efficiently through both ice and the water beneath it. These vibrations produce sounds ranging from sharp snaps to deep, resonant booms. Because ice and water conduct sound well, the noises can travel far, sometimes miles from their source. The effect is strongest on thick, smooth ice under calm conditions. Scientists study these sounds to understand ice thickness, stress, and movement. The vibrations carry information about temperature changes and internal strain. To people nearby, the experience can feel uncanny. Sounds seem amplified or directionless, arriving from across the frozen surface. Winter turns lakes into acoustic instruments. The ice responds to every adjustment, storing and releasing energy audibly. As sound travels across frozen water, winter continues shaping not just landscapes, but the sensory world that surrounds them. Winter can dramatically change how scents move through the air. Cold air is denser and often more stable than warm air, especially during calm conditions. This stability slows the vertical mixing that usually disperses airborne molecules. As a result, odours can linger longer and travel farther near the ground. At the same time, cold temperatures slow many chemical reactions that would normally break scent molecules down. Wood smoke, soil, vegetation, and industrial smells may remain intact for longer periods, creating sharper or more persistent scents. Frost and snow can temporarily trap these molecules on surfaces, releasing them again when sunlight warms the area. Human perception also plays a role. Cold, dry air affects moisture in the nasal passages, subtly changing how smells are detected. Some scents seem muted, while others feel more pronounced because background odors are reduced. Animals respond to these changes as well. Predators and prey adjust movement and behavior when scent trails behave differently than they do in warmer months. Winter reshapes not only what we smell, but how smell itself behaves. The atmosphere becomes a slower conveyor of information. As scent lingers and settles, winter continues altering other invisible signals too, including electromagnetic ones that travel far beyond what our senses can detect. Winter atmospheric conditions can allow radio waves to travel much farther than usual. This occurs when cold air near the ground becomes trapped beneath warmer air above, forming a temperature inversion. These layered conditions bend radio waves back toward Earth instead of letting them escape into the upper atmosphere. Under these circumstances, radio signals can follow curved paths along the surface, extending their range dramatically. Broadcasts may be received hundreds of miles from their source, especially during clear, calm winter nights. Reduced humidity also lowers signal interference, improving clarity. This effect is not limited to human technology. It reveals how electromagnetic energy interacts with the structure of the atmosphere itself. Winter's stable layers act like invisible guides, shaping pathways for energy that normally disperse. Engineers and scientists study these seasonal changes to better understand signal propagation and to design communication systems that remain reliable year-round. Winter quietly reorganizes the air into layered systems that guide sound, scent, light, and radio waves alike. As these invisible pathways form overhead, the frozen ground below continues shaping the movement of heat and energy upward, where winter's influence becomes planetary once again. Winter conditions can make heat leaks in buildings and landscapes far easier to detect. When outdoor temperatures drop well below indoor temperatures, even small sources of warmth stand out sharply against the cold. Heat naturally flows from warmer areas to cooler ones, and winter exaggerates this contrast. Walls, roofs, windows, and foundations release heat at different rates depending on insulation, materials, and construction. In cold air, these differences become visible with thermal imaging, revealing bright patterns where energy escapes. Cracks, gaps, and poorly insulated areas glow clearly, while well-insulated surfaces remain dark. The same effect occurs in natural environments. Warm groundwater springs show through snow. Burrowing animals leave faint thermal traces beneath the surface. Decomposing vegetation releases small amounts of heat that contrast with frozen surroundings. Even recently disturbed soil can appear warmer for a time. Winter simplifies the thermal landscape by removing competing heat sources like sunlight and warm air mixing. What remains is a clean map of energy movement. Researchers, engineers, and wildlife biologists all take advantage of these conditions to study hidden processes. Cold does not create new heat. It reveals where heat already exists. As winter exposes these invisible flows, it also reshapes how frozen water responds to returning sunlight, preparing ice and snow for subtle but powerful transformations. Snow and ice can disappear without ever melting through a process called sublimation. When air is cold but very dry, ice molecules can escape directly into the atmosphere as water vapor. This transition skips the liquid phase entirely. Sublimation occurs most often in winter at high elevations, polar regions, or during clear, windy conditions. Sunlight provides enough energy for ice molecules at the surface to break free, even when temperatures remain below freezing. Wind then carries the vapor away, preventing refreezing. This process can significantly reduce snowpack over time. Snowfields may shrink, edges sharpen, and surface textures change without visible runoff. In mountainous regions, sublimation can remove large amounts of water before spring arrives, influencing river flow months later. Sublimation also cools the surface because energy is absorbed during the phase change. This cooling can slow additional melting, creating a self-regulating effect that prolongs winter conditions locally. Winter demonstrates that disappearance does not require warmth. Cold and dryness are enough. As snow vanishes silently into the air, the atmosphere carries that moisture upward, where it may later return in an entirely different form, continuing winter's slow circulation of energy and matter. Cold winter nights can cause dense air to flow downhill like an invisible liquid. When skies are clear and winds are calm, the ground loses heat rapidly after sunset. The air in contact with it cools, becomes denser, and begins to sink under the influence of gravity. This cold air does not simply settle in place. It drains downslope through valleys, ravines, and low points in the terrain, forming what scientists call cold air drainage flows. These currents can move surprisingly fast and pool in low-lying areas, creating pockets of significantly colder temperatures than surrounding slopes. These cold pools influence frost formation, plant survival, and local weather. Crops in valleys may freeze while hillsides remain unaffected. Fog and frost often appear first in these low zones, shaped by the slow movement of chilled air rather than cloud cover above. Cold air drainage shows that winter air behaves like a fluid, responding to terrain just as water would. The landscape becomes a set of channels guiding temperature itself. As cold air settles and flows across the ground, it shapes microclimates that affect where life can persist, subtly influencing the survival of seeds waiting beneath frozen soil for the moment when winter finally loosens its hold. Winter conditions play a critical role in determining which seeds will successfully grow in spring. Many plants rely on prolonged exposure to cold to trigger internal changes that prepare seeds for germination. This process, known as cold stratification, prevents seeds from sprouting at the wrong time of year. During winter, low temperatures slowly alter hormone balances inside seeds. Protective coatings soften and chemical inhibitors break down. These changes do not cause growth immediately, but they make germination possible once warmth and moisture return. Snow cover supports this process by maintaining stable temperatures. Rather than experiencing damaging temperature swings, seeds beneath snow remain cold but protected. In contrast, seeds exposed to alternating freeze and thaw may be damaged or displaced. Frozen soil also shifts seed position. Expansion and contraction can bury some seeds deeper while lifting others closer to the surface. These movements influence which plants gain access to light and moisture first in spring. Winter quietly filters future ecosystems. Long before leaves emerge, cold determines which species are ready to rise. As seeds rest in prepared silence, frozen ground continues storing energy that will soon release through meltwater, carrying winter's influence into the next season. Winter snow cover can strongly influence how groundwater is recharged beneath the surface. When snow accumulates, it stores water in a frozen form while insulating the soil below. This insulation often keeps deeper ground from freezing solid, allowing some subsurface pathways to remain open. As temperatures rise, snow melts gradually rather than all at once, especially in shaded or forested areas. Meltwater does not always run directly into streams. Instead, it can seep into the soil at specific entry points where frozen layers thin or crack. These locations become gateways through which water descends into aquifers. Frozen subsurface layers can also redirect water sideways. If deeper soil remains frozen, meltwater spreads laterally before finding a downward route. Over many seasons, this repeated pattern carves preferred pathways underground, shaping how groundwater moves long after winter ends. Hydrologists study snowmelt closely because it controls water availability months into the future. A winter with deep, slow-melting snowpack replenishes groundwater more effectively than one dominated by rapid thaws. Winter therefore acts as a planner rather than a provider, deciding where water will go before it ever flows. As this hidden routing unfolds below ground, frozen surfaces above continue recording motion and pressure in delicate ways, including the preservation of fleeting marks made by passing life. Frozen ground and snow can preserve animal tracks with remarkable clarity. When an animal steps onto moist soil or thin snow during cold conditions, pressure forces water upward around the imprint. As temperatures fall, this moisture freezes, locking the shape into place. The result is a durable cast that can survive for days or even weeks. Fine details such as claw marks, toe spacing, and stride length may remain visible long after the animal has moved on. Additional snowfall can bury these tracks, but the frozen imprint beneath often remains intact until thaw. Wildlife biologists and trackers rely on these preserved tracks to study movement patterns, territory boundaries, and population presence without direct observation. Winter landscapes become quiet records of activity that would otherwise go unnoticed. The same process can preserve human footprints, tire tracks, and tool marks, turning frozen ground into a temporary archive of motion. This preservation is fragile. Once temperatures rise, the ice binding the imprint melts and the record disappears quickly. Winter offers a brief window where movement becomes memory. As tracks fade and meltwater returns to the soil, winter continues reshaping materials themselves, revealing how familiar substances respond when cold alters their internal structure. Freezing temperatures can dramatically change the physical behavior of common materials. Rubber that bends easily in warm weather becomes stiff and brittle in deep cold. Plastics lose flexibility as molecular motion slows, making them more likely to crack or fracture under stress. Metals also respond to winter conditions. As temperatures drop, metal contracts slightly, tightening joints and altering tolerances in mechanical systems. Repeated cold exposure can produce audible creaks as structures adjust to shrinking components. Even glass behaves differently. Rapid temperature changes can create internal stress, increasing the risk of cracking if one area warms faster than another. Lubricants thicken in cold conditions, slowing moving parts and increasing wear. These changes occur because cold reduces thermal energy at the molecular level. Atoms vibrate less, and materials become less forgiving when forced to move or bend. Engineers design winter-rated materials to account for these effects, choosing compositions that remain stable across temperature extremes. Winter reveals that material properties are not fixed traits, but conditional behaviors shaped by environment. As solids stiffen and contract, the cold continues influencing forces far larger than individual objects, including how entire snow-covered regions interact with sunlight and energy from above. Winter sunlight interacts with snow in ways that dramatically reshape how energy moves across the surface of the Earth. Fresh snow reflects a very high percentage of incoming sunlight, far more than soil, vegetation, or water. This reflectivity sends much of the sun's energy back into the atmosphere rather than allowing it to warm the ground. Because less energy is absorbed, snow-covered areas remain cooler, reinforcing cold air above them. This creates a feedback loop where cold preserves snow and snow preserves cold. On a regional scale, widespread snow cover can strengthen high-pressure systems and influence weather patterns far beyond the snowy area itself. The brightness of snow also changes human and animal experience. Increased reflection can cause glare and eye strain, while at the same time making distant features appear sharper and more defined. Landscapes gain contrast, even under low winter sun angles. This reflective behavior plays a measurable role in climate systems. Scientists track seasonal snow cover carefully because small changes can affect temperature trends and atmospheric circulation. Snow does not simply rest on the ground, it actively participates in energy exchange. As sunlight is redirected upward, the atmosphere above becomes more stable, setting conditions where frozen air continues shaping how particles, moisture, and ice crystals behave high overhead. Winter clouds often contain far more ice than liquid water. At cold temperatures, even droplets that remain liquid exist in a supercooled state, ready to freeze with minimal disturbance. Once ice crystals begin forming, they grow rapidly by attracting water vapor more efficiently than liquid droplets can. This process, known as the Bergeron-Findeisen process, causes ice crystals to grow at the expense of surrounding droplets. Over time, clouds become dominated by ice rather than liquid. The shape of these crystals depends on temperature, producing plates, needles, columns, or branching forms. Ice-rich clouds behave differently from warm clouds. They scatter sunlight more sharply, contribute to optical displays like halos, and produce snow instead of rain. Even when surface temperatures are above freezing, winter clouds aloft may still be primarily frozen. The presence of ice changes how precipitation forms and falls. Crystals can collide, stick together, and grow large enough to descend as snowflakes or sleet. Winter clouds therefore operate under a different internal chemistry than summer ones. As frozen particles drift within them, they prepare the atmosphere for precipitation that settles quietly below, adding new layers to the snowpack that will continue evolving long after the clouds themselves have passed. Snow grains do not remain unchanged after they fall. Once on the ground, snow undergoes continuous transformation through a process called metamorphism. Temperature differences within the snowpack cause water vapor to migrate from warmer layers near the ground toward colder layers near the surface. As vapor moves, snow grains change shape. Rounded grains may become angular and faceted. Bonds between crystals may strengthen or weaken depending on conditions. Over time, the snowpack develops layers with distinct mechanical properties. These changes influence how well snow supports weight, how it insulates the ground, and how it responds to stress. In mountainous regions, snow metamorphism plays a critical role in avalanche formation, as weak layers can collapse under added load. Sunlight, air temperature, depth, and moisture all shape this ongoing evolution. Snow that looks static is, in fact, constantly reorganizing at the microscopic level. Winter reveals that stillness does not mean inactivity. Even when landscapes appear frozen and quiet, energy and matter continue moving slowly within the snow, preparing it for the moment when warmth returns and transformation accelerates once again. Freezing fog can transform directly into ice crystals while suspended in the air. In very cold conditions, fog droplets may remain liquid even when temperatures are well below freezing. These supercooled droplets hover quietly until they encounter dust, ice, or even slight disturbances. When freezing begins, the fog changes almost instantly. Liquid droplets crystallize mid-air, becoming countless tiny ice particles that drift slowly downward. The The transformation can turn an ordinary grey fog into a glittering field of falling crystals that sparkle in sunlight or glow around streetlights at night. This process often coats nearby surfaces as well. Trees, wires and buildings collect the crystals, forming delicate frost that grows outward in the direction of airflow. Unlike snowflakes formed high in clouds, these crystals originate close to the ground, shaped by stillness rather than turbulence. Freezing fog reveals how thin the boundary can be between liquid and solid. A subtle change in temperature or motion is enough to shift the entire state of the atmosphere. As these crystals settle, they join the snowpack below, adding another layer shaped not by storms, but by calm air and quiet cold, where chemistry and light continue interacting just above the surface. Winter storms can lift tiny particles high into the atmosphere, sometimes reaching the stratosphere. Powerful updrafts form within large cold season systems as strong temperature contrasts drive air upward. These rising currents can carry dust, sea salt, ash, and organic material far above typical cloud heights. Once particles reach these altitudes, they may remain suspended for long periods. The stratosphere lacks the turbulent mixing found closer to the surface, allowing material to spread across vast distances. Some particles influence atmospheric chemistry or affect how sunlight is absorbed and reflected. Scientists study these events to understand how winter storms contribute to long-range transport of matter. Materials lifted during a single storm can cross continents or oceans before settling back toward Earth. Winter storms therefore do more than redistribute heat. They also move physical matter into regions of the atmosphere that shape climate processes on a global scale. As these particles drift slowly above the planet, the frozen ground below continues recording winter's influence in quieter ways, including the preservation of impressions left by brief moments of contact between life and ice. Frozen soil and thin ice can preserve footprints with extraordinary precision. When pressure is applied to moist ground in cold conditions, water is forced upward around the impression. As temperatures drop, that moisture freezes, forming a rigid mold of the shape. These frozen impressions can capture fine details such as tread patterns, toe placement, and stride length. Once sealed, they may persist for weeks, even if fresh snow falls above them. The record remains hidden but intact until thaw breaks it apart. Researchers use these preserved tracks to study wildlife behavior without direct observation. The frozen ground becomes a temporary archive of movement, storing evidence of presence long after the moment has passed. This preservation is brief but powerful. When temperatures rise, the ice binding the imprint melts quickly and the record vanishes. Winter offers moments where motion becomes memory. As tracks fade back into soil and snow, the same freezing processes continue shaping water itself, guiding how ice forms structures that influence light, sound, and energy across the winter landscape. Ice can form layered structures that store a precise record of changing winter conditions. When freezing occurs in stages rather than all at once, distinct layers of ice develop with different textures, strengths, and optical properties. Calm, clear nights often produce smooth, transparent ice, while later freezing during wind or snowfall traps air bubbles and impurities, creating cloudy layers above or below. These layers expand and contract at different rates as temperatures fluctuate. Stress builds along their boundaries, producing faint popping sounds or subtle shifts that release energy without visible cracking. Sunlight penetrates each layer differently, creating variations in brightness and color that reveal the ice's internal structure. On lakes and rivers, layered ice influences how cracks spread and how sound travels across the surface. The lower layers may support weight while upper layers remain fragile. Scientists study these differences to understand freeze timing and ice safety. Each layer corresponds to a specific set of weather conditions. Ice becomes a seasonal archive, preserving calm, wind, snowfall, and temperature swings in frozen form. Winter quietly records itself in these stacked structures. As layered ice continues adjusting to cold and light, it prepares the stage for interactions with gas and chemistry beneath the surface, where winter traps invisible materials long before they are released again. Frozen lakes can trap methane gas beneath clear ice, forming visible domes and bubbles. Methane is produced when microorganisms break down organic material at the lake bottom. In warm seasons, this gas escapes easily into the atmosphere. In winter, ice seals the surface, preventing release. As methane rises, it becomes trapped under the ice, pushing upward and stretching the frozen surface into curved shapes. In very clear ice, stacked bubbles appear like frozen pearls, marking repeated releases over time. Each layer represents a separate pulse of biological activity beneath the ice. These trapped gases remain isolated throughout winter. When spring arrives and the ice weakens, the methane is released rapidly into the air. Scientists study these formations to understand seasonal gas cycles and how winter storage affects atmospheric chemistry. The bubbles also reveal that biological processes continue even when the surface appears lifeless. Beneath ice, microbes remain active, slowly producing gas in dark, cold conditions. Winter does not stop exchange between Earth and atmosphere, it delays it. As methane waits beneath ice, the frozen surface above continues shaping how light passes through water, turning lakes into temporary lenses that distort and magnify the world below. Clear winter ice can bend and focus light, creating natural optical lenses. When water freezes slowly and without trapped air, the resulting ice becomes transparent and smooth. Curved surfaces on frozen lakes, icicles, or refrozen meltwater can refract sunlight in precise ways. These ice lenses magnify objects beneath them, distort shapes, or concentrate light into bright patches that shift as the sun moves. Stones, plants, or cracks below the ice may appear stretched or floating, transformed by the way light travels through the frozen surface. In rare cases, concentrated sunlight passing through clear ice can warm small areas beneath it more quickly than surrounding regions. While uncommon, this effect demonstrates how ice can act not only as insulation, but also as an optical tool. Winter landscapes therefore host quiet experiments in physics. Light interacts with frozen water in ways that reveal its wave-like behavior and sensitivity to shape and clarity. As ice bends sunlight and reshapes vision, winter continues reminding us that even in stillness, energy moves, transforms, and prepares for the moment when frozen systems begin to release their stored motion back into the flowing world. Snow cover can dramatically change how animals communicate and detect one another. Fresh snow alters the physical environment through which sound and scent travel. High-frequency noises are absorbed by soft snow, while lower frequencies reflect more efficiently across frozen surfaces. This reshapes the acoustic landscape that animals rely on for calls, warnings, and navigation. Cold air also carries sound differently. Dense winter air allows certain calls to travel farther, while others fade quickly. As a result, many animals adjust the timing, pitch, or duration of their vocalizations, favoring conditions when wind is low and sound transmission is more reliable. Scent behaves differently as well. Snow can trap odor molecules beneath its surface, interrupting scent trails that predators often depend on. This forces hunters to rely more on hearing or sight, while prey gain brief windows of reduced detectability. Over time, both sides adjust movement patterns to account for these sensory changes. Winter does not silence ecosystems, it rewires them. Information still moves, but through altered channels shaped by cold, snow, and air density. As communication adapts to frozen conditions, the physical environment continues influencing survival in other ways, including how snow itself reshapes temperature patterns near cities and human structures. Snow cover can significantly influence temperatures in and around cities. When snow blankets open land near urban areas, it reflects sunlight that would otherwise warm the ground. This cooling effect allows cold air to persist longer and drift into nearby populated regions. Cities usually remain warmer than their surroundings due to heat retained by buildings, roads, and human activity. Snow can weaken this urban heat island effect by reducing heat absorption during daylight hours. Snow-covered parks, fields, and riverbanks act as cold reservoirs that influence local air circulation. At night, snow limits heat release from surfaces, further stabilizing cold air. This can lower overnight temperatures and change wind patterns across neighborhoods. As snow melts, moisture released into the air can also influence humidity and fog formation. Meteorologists monitor snow extent because its presence alters energy exchange on a regional scale. Even temporary snow cover can change daily weather behavior. Winter snow does not stop at the edge of cities. It becomes part of their climate system. As temperature patterns shift at the surface, frozen air above responds in kind, shaping pressure differences that guide larger atmospheric motion. Winter pressure patterns play a major role in shaping regional climates. As land cools rapidly during cold months, dense air settles and creates high-pressure systems that can persist for days or weeks. These systems influence wind direction, storm paths, and temperature distribution across large areas. High pressure often brings clear skies and calm conditions, allowing further cooling at night. Low-pressure systems, by contrast, draw in warmer, moister air and generate storms that redistribute heat and precipitation. The position and strength of these systems determine whether a region experiences prolonged cold, snowfall, or temporary warming. Small shifts in pressure placement can have large effects. A slight movement of a winter high-pressure zone can redirect storms hundreds of miles away, altering precipitation patterns far downstream. These dynamics help explain why winter weather can feel locked in place or suddenly change course. Scientists study winter pressure behavior to understand long-term climate variability. These systems link local cold to global circulation. As pressure shapes air movement overhead, the frozen surface below continues responding in quieter ways, where ice and snow store energy, waiting for the moment when winter begins its gradual release. Frost can grow into intricate patterns that map air flow across a surface. When moist air comes into contact with a surface that is below freezing, water vapor condenses and freezes instantly. As ice crystals begin to form, their growth is guided by tiny temperature differences and subtle movements of air. Rather than spreading evenly, frost follows invisible pathways. Warmer areas remain clear longer, while colder spots attract rapid crystal growth. Gentle air currents from heaters, vents, or even a person moving nearby can redirect the frost, causing branching shapes, spirals, and feather-like forms to emerge. Microscopic imperfections on glass, metal, or stone act as starting points where crystals anchor and expand outward. Once growth begins, each new crystal alters airflow slightly, influencing the direction of the next. The result is a frozen record of heat transfer and air motion. No two frost patterns are identical because the conditions that create them are always changing. Each surface becomes a temporary map of its environment. Winter reveals complex motion in what looks like stillness. As frost traces invisible air currents, it quietly demonstrates how cold turns everyday surfaces into instruments that record energy moving through space. Winter conditions can create mirage-like distortions normally associated with deserts. When extremely cold, dense air rests near the ground with warmer air above it, light bends as it travels through these layers. Objects may appear lifted, stretched, or duplicated near the horizon. Snow-covered landscapes enhance this effect by cooling the air evenly and reducing turbulence. Distant trees, buildings, or mountains can seem taller or closer than they truly are. In rare cases, objects hidden below the horizon become visible through a phenomenon known as looming. These winter mirages rely on stability. As soon as wind mixes the air or temperatures equalize, the illusion fades. Because winter air is often clear and dry, the distortions can appear sharp rather than hazy. The physics behind these effects is identical to hot weather mirages, but reversed in temperature. Cold replaces heat as the driving force. Winter quietly rearranges perception itself. As light bends through frozen air, it reminds us that what we see depends on invisible structures shaped by temperature and balance. Winter can slow biological processes across entire ecosystems to near suspension. As temperatures drop, chemical reactions inside living organisms proceed more slowly. Enzymes become less active, energy demands decrease, and growth halts or nearly halts in many species. Plants shift into dormancy, reducing metabolic activity and conserving resources. Microorganisms slow their breakdown of organic matter, altering nutrient cycles for months at a time. Predators hunt less frequently, prey move less, and the overall flow of energy through food webs becomes subdued. This slowdown is not failure or collapse. It is a coordinated pause that protects systems from stress during periods of limited resources. Cold provides stability by limiting rapid change. When warmth returns, reaction rates increase quickly. Dormant systems awaken almost simultaneously, producing the sudden surge of activity that defines spring. Winter acts as a natural reset, pressing pause on life without stopping it entirely. As biological motion slows and quiet spreads across the landscape, the season prepares living systems for renewal, guiding them gently toward the final truths winter reveals before giving way to what comes next. Snow can store detailed chemical records of the atmosphere long after it falls. As snowflakes form and descend, they collect tiny particles from the air, including dust, sea salt, pollen, industrial pollutants, and trace gases. Each snowfall captures a snapshot of atmospheric conditions at that moment. Once on the ground, these materials remain embedded within the snowpack. Because cold temperatures slow chemical reactions, many compounds remain relatively unchanged throughout winter. Layer by layer, snow accumulates a vertical archive of airborne material that scientists can later analyze. When researchers dig snow pits, they can identify subtle bands where chemistry shifts. A darker line might indicate distant wildfire smoke. Elevated salts can point to ocean storms. Changes in nitrogen compounds may reflect human activity or natural soil emissions. As snow melts in spring, these chemicals are released into soil and waterways, influencing nutrient cycles and water quality. Winter therefore delays chemical movement, storing it temporarily before redistributing it all at once. Snow is not just frozen water. It is a collector and carrier of atmospheric history. As these chemical traces rest quietly through winter, they prepare to re-enter the living world, linking cold skies above to biological activity that resumes below. Winter can dramatically sharpen long-distance visibility. Cold air holds far less moisture than warm air, reducing haze caused by water droplets. When skies are clear and winds are calm, the atmosphere becomes unusually transparent. With fewer particles scattering light, distant mountains, buildings, and landscapes appear crisp and sharply defined. Snow-covered ground further enhances this clarity by reflecting light upward, illuminating features that might remain hidden during other seasons. Temperature inversions also play a role. Stable layers of air limit turbulence, preventing dust and pollutants from mixing upward. The result is a still, clean visual corridor that allows the eye to see far beyond its usual range. These conditions are often most noticeable after winter storms, when snowfall has scrubbed particles from the air. The world feels suddenly expanded, horizons pulled closer. Winter trades comfort for clarity. The cold strips away visual noise, revealing structure and distance with precision. As vision sharpens across frozen landscapes, attention naturally drifts upward again, towards skies where winter continues shaping clouds, light, and the final movements of energy before the season slowly begins to loosen its grip. Winter temperature swings can carve patterns into rock through repeated freezing and thawing. When water seeps into small cracks during mild periods, it expands as it freezes, exerting pressure on the surrounding stone. Over time, this pressure widens fractures and loosens fragments. The process is gradual but persistent. Each freeze-thaw cycle adds a small change, and over many winters, rock surfaces flake, split, and break apart. This mechanism contributes to the formation of loose soil, scree slopes, and weathered cliffs. Rocks with existing weaknesses are especially vulnerable. Tiny imperfections become starting points for larger fractures. In regions where winter temperatures frequently cross the freezing point, this form of weathering becomes one of the dominant forces shaping the landscape. Winter does not need dramatic motion to reshape stone. It works through patience and repetition. Quiet nights and subtle temperature shifts do the work. As rock slowly yields to cold, winter reminds us that even the most solid materials are temporary. With this final lesson in persistence and change, the season gently prepares the mind for rest, where stillness becomes the most powerful force of all. When winter snow begins to melt, it can release a sudden pulse of stored chemicals into soil and waterways. Throughout the season, snowpack quietly accumulates particles and gases from the atmosphere, including nutrients, salts, and pollutants. Cold temperatures slow reactions, allowing these materials to remain concentrated within the layers. As melting starts, water does not always drain evenly. Early meltwater often flushes the upper layers first, carrying a higher concentration of dissolved substances than later flows. This phenomenon, sometimes called an ionic pulse, delivers a brief but intense chemical input to streams, lakes, and soils. Aquatic ecosystems are especially sensitive to this timing. Sudden changes in acidity or nutrient levels can affect microorganisms, algae growth, and oxygen balance. On land, soils receive a concentrated dose of nutrients that can influence plant growth patterns in early spring. Scientists monitor snowmelt chemistry to understand water quality and ecosystem response. The same snow that insulated and preserved winter landscapes becomes a vehicle for rapid change once temperatures rise. Winter, therefore, delays chemistry rather than eliminating it. What is stored quietly for months is released quickly, carrying winter's imprint forward. As meltwater moves away, frozen oceans continue holding their own hidden structures, where ice behaves less like a solid sheet and more like a living network. Sea ice is not a solid block of frozen water, but a complex structure filled with liquid channels. As ocean water freezes, salt is mostly excluded from the forming ice. The rejected salt concentrates into narrow pockets and pathways called brine channels, which remain liquid even in extreme cold. These channels weave through the ice, creating a network of salty fluid that moves slowly as temperatures change. When conditions warm slightly, the channels widen, allowing brine to drain into the ocean below. When temperatures drop, they narrow again, trapping liquid in place. Surprisingly, these brine channels host microscopic life. Algae and bacteria adapted to cold, salty conditions thrive within them, forming tiny ecosystems inside the ice. These organisms contribute to polar food webs when spring melt releases them into the ocean. The chemistry of brine channels also influences ocean circulation. Dense, salty brine sinking from forming ice can drive currents that help move water masses around the globe. Winter sea ice is therefore active rather than inert. It exchanges salt, heat, and life with the ocean beneath it. As these hidden pathways shift and drain, the ice above responds to stress and motion, sometimes releasing energy in ways that can be heard across frozen expanses. Large sheets of winter ice can release energy in vibrations that resemble small seismic events. As ice expands and contracts with temperature changes, stress builds within the frozen surface. When that stress exceeds the ice's strength, it is released suddenly through cracks or shifts. These releases send vibrations traveling through ice and into the ground or water below. Sensitive instruments often detect them as tiny quakes, even though they originate in ice rather than rock. The sounds associated with these events range from sharp cracks to deep, resonant booms. Such vibrations provide scientists with valuable information. By analyzing their frequency and movement, researchers estimate ice thickness, stress distribution, and the rate at which ice responds to environmental change. In polar regions, similar signals help monitor ice shelves and glaciers. To human ears, these sounds can feel uncanny, arriving without visible motion. They remind us that frozen landscapes are not silent or static. Winter stores energy in tension, not stillness. When that energy releases, it echoes across ice and air alike. As these quiet vibrations fade, winter continues toward its final truths, where even the coldest systems begin preparing to soften, slow, and let go. Winter oceans continue moving beneath ice, even when the surface appears completely still. Currents do not stop when water freezes. Instead, they flow quietly below the ice, guided by differences in temperature, salinity, and density. These slow movements redistribute heat and nutrients throughout the water column. As sea ice forms, the process of freezing releases salt into the surrounding water, increasing its density. This heavier water sinks, driving vertical circulation that connects surface conditions to deeper layers. In some regions, this sinking motion contributes to large-scale ocean currents that influence climate far beyond polar zones. Beneath frozen lakes and seas, life responds to these movements. Nutrients transported by currents support microorganisms, which in turn sustain larger organisms when light returns. Winter circulation quietly sets the stage for spring productivity. The frozen surface hides this activity, giving the impression of rest. In reality, motion continues at a slower, steadier pace, shaped by physics rather than weather. Winter reminds us that stillness is often an illusion. Beneath ice, energy continues flowing, Above it, frozen air prepares to guide that energy upward again, where winter reshapes the atmosphere one final time before releasing its hold. Cold winter air can dramatically alter how electromagnetic energy interacts with the atmosphere. Temperature differences between air layers change density, which in turn affects how waves move through space. In winter, stable layers often form that guide energy along curved paths instead of allowing it to disperse freely. These effects influence more than radio signals. Radar performance, satellite observations, and even the way certain frequencies scatter in the atmosphere are shaped by winter air structure. Clear, dry conditions reduce interference, while inversions create reflective boundaries. Scientists take advantage of winter conditions to study atmospheric physics because fewer variables are in motion. Reduced humidity, weaker convection, and stable layering simplify observations and reveal underlying patterns that remain hidden in summer turbulence. Winter acts as a natural laboratory. The atmosphere becomes quieter, slower, and more predictable, allowing energy pathways to stand out. As electromagnetic signals bend and travel through cold air, winter shows that even invisible forces respond to temperature. And as these forces move overhead, the season approaches its quiet conclusion, where stored energy begins preparing for release. As winter progresses, the balance between stored energy and restraint becomes increasingly delicate. Snowpack holds water, ice stores tension, and cold air traps motion close to the surface. These systems remain stable only while temperatures stay low. Small changes begin to matter more. A few degrees of warming can weaken ice bonds, open pathways in snow, or disrupt atmospheric layers. Winter systems are resilient, but not rigid. They are designed to hold, not to last forever. This sensitivity is what allows spring to arrive so quickly once conditions shift. Energy that was slowed and stored is released in coordinated ways. Meltwater flows, air mixes, life accelerates. Winter is therefore not an ending, but a controlled pause. It gathers motion, limits chaos, and prepares systems for rapid change. The quiet you feel is not emptiness, but readiness. As the season gently loosens its grip, the mind can do the same. With just a few truths remaining, winter's story begins to close, leaving behind calm, clarity, and the soft understanding that stillness itself is a form of movement. As winter deepens, daylight shortens in a predictable rhythm governed by Earth's tilt. The planet's axis leans about 23.5 degrees, causing one hemisphere to receive less direct sunlight during winter months. This tilt changes not only how long the sun stays above the horizon, but also the angle at which its light arrives. Lower sun angles mean sunlight spreads across a larger surface area, delivering less energy per square meter. Even on clear days, winter sunlight feels weaker because it travels through more atmosphere and strikes the ground obliquely. Shadows stretch longer and warming slows. These changes influence biological clocks. Many plants and animals respond more strongly to day length than temperature. Hormone production, feeding behavior, and sleep cycles adjust based on the gradual shortening of daylight rather than sudden cold. Humans experience this rhythm as well. Reduced daylight alters melatonin production, subtly encouraging rest and introspection. Winter's slower pace is written into the sky itself. The shortening day is not a loss, but a signal. It marks the period when Earth is storing energy rather than spending it. As daylight reaches its minimum, winter settles into its quietest point, preparing for the slow return of light that will eventually unlock everything it has held in place. The winter solstice marks the moment when daylight reaches its shortest duration and begins to lengthen again. It occurs when one hemisphere is tilted farthest away from the sun. Although temperatures often continue dropping afterward, the balance of light has already shifted. From this point forward, each day gains a small amount of sunlight. The change is subtle at first, often imperceptible, but it is steady and irreversible. Ancient cultures tracked this moment carefully, recognizing it as a turning point rather than the depth of winter. Physically, the solstice does not bring immediate warmth. Snow, ice, and cold air persist because Earth's surface and oceans release stored heat slowly. But energetically, the system has begun transitioning. The pause has reached its limit. Winter's restraint is now paired with promise. Light returns before warmth does, offering information before action. This separation allows ecosystems to prepare without rushing, ensuring stability as change approaches. The solstice is a reminder that cycles operate on patience. Even at maximum stillness, motion has already resumed. As light begins its slow climb, winter's role shifts from holding to releasing, guiding the mind gently toward the final quiet lessons of the season. Winter's stillness can enhance the brain's ability to settle into slower patterns of thought. Reduced daylight, quieter environments, and limited external stimulation encourage neural rhythms associated with rest and reflection. Studies show that lower light levels increase melatonin production, promoting sleep and reducing alertness. Cold also reduces outdoor activity for many people, decreasing sensory input. Fewer sounds, muted colors, and slower movement create an environment with less cognitive demand. The brain responds by shifting toward internal processing rather than constant reaction. This does not mean winter dulls the mind. Instead, it changes its focus. Memory consolidation, imagination, and emotional regulation benefit from reduced stimulation. The nervous system gains space to recalibrate. Nature mirrors this pattern. Ecosystems slow, organisms conserve energy, and systems stabilize. Human physiology follows the same principles, even in modern environments. Winter offers permission to rest without urgency. It demonstrates that pause is productive, that quiet supports balance. As the season continues releasing its stored light and energy, the mind can remain calm, knowing that nothing is missing. Only a few truths remain now, and they will arrive gently, like the gradual lengthening of days that begins almost too softly to notice. Winter slows the global water cycle, stretching time between evaporation and precipitation. Cold temperatures reduce evaporation from oceans, lakes, soil, and vegetation. Water molecules require energy to escape into the air, and winter simply provides less of it. As a result, the atmosphere holds less moisture overall. With reduced evaporation, clouds form more slowly and contain less water. Precipitation becomes less frequent, but often more structured, falling as snow rather than rain. Snow stores water where it lands, delaying its movement through the system. Instead of flowing immediately back to rivers and oceans, water pauses on the surface for weeks or months. This slowdown stabilizes the climate system. Sudden transfers of heat and moisture are reduced, allowing energy differences between regions to rebalance gradually. Winter acts like a regulator, easing the pace of circulation rather than stopping it. The delayed return of water also shapes ecosystems. Plants and soil organisms wait, conserving resources until meltwater arrives. Rivers plan their future flow based on snowpack rather than storms. Winter stretches the journey of water, reminding us that cycles are not only about movement, but timing. As moisture waits in frozen form, the planet breathes more slowly, preparing for the steady inhale that arrives with warming light. Ice and snow can reduce vibration and motion across the landscape, creating a quieter physical world. Snow absorbs mechanical energy efficiently because its structure is filled with air pockets. When vibrations travel through it, energy disperses quickly instead of reflecting or amplifying. This dampening effect influences more than sound. Ground vibrations from wind, movement, or machinery are softened. Trees sway less sharply, soil transmits fewer shocks, and even minor seismic vibrations are slightly muted near the surface. Ice also constrains motion by locking components in place. Loose rocks, soil grains, and organic material become bound together, reducing friction-based movement. Winter landscapes therefore experience fewer small disturbances, allowing systems to remain stable for longer periods. This reduction in motion contributes to winter's sense of calm. With fewer vibrations traveling through ground and air, the environment feels settled and contained. Energy remains stored rather than spent. Winter shows that stillness can be engineered by structure. By changing how matter connects, cold reduces unnecessary motion. As vibration fades, attention turns inward, preparing both landscapes and minds for the final transition from holding to release. As winter nears its end, the balance between restraint and motion becomes increasingly fragile. Snowpack holds water, ice stores tension, and cold air maintains layered stability. These systems coexist in equilibrium only within a narrow temperature range. A slight increase in sunlight or a modest shift in air mass can tip the balance. Bonds weaken, layers mix, and pathways reopen. What changes first is not always visible. Ice may soften internally before cracking. Snow may begin channeling meltwater long before shrinking noticeably. Air may destabilize before winds rise. Winter's final phase is defined by readiness rather than action. Energy is still restrained but no longer locked. Systems prepare to transition smoothly rather than collapse abruptly. This design prevents chaos. The gradual release ensures rivers flow instead of flood, ecosystems wake instead of shock, and atmospheres mix instead of overturn violently. Winter teaches that endings do not arrive suddenly. They unfold through preparation. As restraint gives way to motion, the season completes its role, leaving behind balance rather than emptiness. With only a few truths remaining, everything that has been held now knows how to move again, gently and without urgency. As winter loosens its hold, snow begins to change internally before it visibly melts. Long before the surface collapses, sunlight penetrates the snowpack and warms specific layers unevenly. This creates narrow channels where liquid water starts to move through frozen grains, even while the snow still looks solid from above. These internal pathways guide meltwater downward and outward. The snowpack becomes less like a blanket and more like a sponge, directing water towards specific exit points. This hidden movement determines where water will emerge, which soils will saturate first, and which streams will swell earliest. Because this change happens quietly, it often goes unnoticed. Yet it is one of winter's most important transitions. Snow shifts from storage to transport, from holding to releasing. The structure that once resisted motion now facilitates it. This slow internal change prevents sudden collapse. By the time snow visibly shrinks, much of the work has already been done beneath the surface. Winter shows that transformation begins invisibly. What looks unchanged may already be moving. As snow prepares to let go, ice nearby undergoes a similar internal shift, where strength fades gradually rather than breaking all at once. Ice weakens from the inside before it fractures on the surface. As temperatures rise slightly or sunlight increases, microscopic bonds within ice begin to loosen. The ice may still appear thick and solid, but its internal structure becomes more flexible and less able to store stress. This change alters how ice responds to pressure. Instead of cracking sharply, it may bend, absorb vibration, or fail suddenly without warning. Internal melting along grain boundaries reduces overall strength well before visible thinning occurs. Scientists measure this process to understand ice safety and seasonal transitions. Thickness alone does not determine stability. Temperature history and internal structure matter just as much. Winter ice does not end with dramatic breakage. It softens first, preparing to release stored tensions smoothly rather than violently. This gradual weakening mirrors winter's broader design. Systems do not fail abruptly, they transition. As ice releases its grip, air above also begins changing character, losing its rigid layers and preparing to mix freely once again. As winter approaches its final phase, atmospheric layers begin to destabilize. Temperature inversions weaken, allowing air to mix vertically once more. Moisture spreads more evenly, winds increase, and the atmosphere regains its three-dimensional movement. This mixing redistributes heat and chemical components that were trapped near the surface for months. Pollutants disperse, humidity rises, and clouds reform more easily. The sky becomes more dynamic, signaling the end of winter's restraint. These changes do not happen all at once. Calm days may still appear, but the underlying structure has shifted. The atmosphere is no longer holding energy in place. It is preparing to move it. Winter's influence fades not through disappearance, but through integration. What was separated reconnects. What was stored begins circulating again. With the atmosphere ready to move, the season has completed its work. Only a final truth remains, not about cold or snow, but about the role winter plays in allowing rest to exist without guilt and change to arrive without force. Winter creates a rare state of environmental synchronization, where many natural systems slow together rather than independently. Temperature, light, water movement, biological activity, and atmospheric motion all reduce their pace at the same time. This alignment is unusual. In most seasons, one system accelerates while another lags behind. In winter, restraint becomes shared. Because of this synchronization, changes propagate more gently. Rivers wait for snowmelt. Plants pause growth until daylight returns. Animals conserve energy in parallel. Even chemical reactions slow across soils, water, and air. The entire system agrees, briefly, to wait. This coordination reduces conflict between processes. There is less competition for resources, fewer abrupt shifts, and fewer mismatches between supply and demand. Winter creates stability not by force, but by timing. Everything slows enough to remain aligned. Scientists observe that ecosystems emerging from synchronized slowdowns tend to rebound more efficiently. Spring activity unfolds smoothly because systems awaken together rather than in isolation. Winter's pause prevents fragmentation. This shared slowing offers a model for balance. It shows that rest works best when it is collective rather than resisted. As winter completes this synchronization, it prepares the conditions for renewal that feels natural instead of rushed, guiding all systems toward motion that arrives together, calmly and without strain. Winter's final role is not to end, but to complete a cycle of restraint that makes renewal possible. By slowing movement, storing energy, and quieting systems, winter creates the conditions necessary for change to occur without damage. Nothing is wasted, everything is held. Snow stores water, ice stores tension, cold air stores stability. Biological systems store potential. When release begins, it happens gradually because winter has already done the work of preparation. This is why spring can arrive quickly without chaos. The groundwork was laid in silence. From a physical perspective, winter demonstrates that energy does not disappear when motion slows. It redistributes. It waits. Systems remain active beneath the surface, operating at lower intensity but with higher efficiency. Rest is not absence, it is conservation. This principle extends beyond nature. Winter reflects a universal pattern where slowing down allows systems to reset without breaking. Stability comes not from constant motion, but from knowing when to pause. As the season completes its work, nothing needs to be forced. Light returns, water flows, life accelerates, and the quiet purpose of winter dissolves gently into motion, leaving behind balance, continuity, and the deep calm that comes from understanding that stillness was never emptiness at all. Thank you for spending this quiet time with me. Winter reminds us that slowing down is part of staying balanced, that rest prepares us for what comes next. If your thoughts feel softer now, let them drift. There is nothing else to do. Good night.